Porus Supercomputing, we're working with Sandia Labs to create a supercomputer cluster. My name is Zach.
I'm Sean.
I'm Eric.
I'm Will. I'm Nate.
I'm Jared.
So the basis of our project is the NVIDIA Jetson board, which uses a quad-core CPU and integrated NVIDIA graphics processor. Our mission is to create a low-cost, low-power, high-performance supercomputer cluster using these boards. Our task is to determine the setup, the board management, the system monitoring, and then benchmarking the system. But the most important thing is documentation, because that's the information that Sandia needs. Our main client is Sandia National Labs, who is financing this. They're interested in lowering the energy costs of their supercomputers. Our secondary contact is Dr. Chris Whitcomb, who is a professor of parallel computing here at Poly. Our final contact is graduate student Gavin Baker, who helped us with CUDA and our initial development. Our other stakeholders include research groups, because research groups use supercomputers to various research groups use supercomputers to run complex simulations, and reducing the costs of supercomputers increases accessibility to compute time on these systems. Also, reducing the power usage of supercomputers reduces the impact on the environment. For our objectives start with selecting the components we need for our system, which means evaluating all our options to find the best components to build our system. We need to document everything during our setup, which includes everything that does and does not work. And finally, we need to benchmark the system with performance versus power usage for different cluster sizes. Now requirements for me.
Alright, so our marketing requirements. First thing is to create a low power, low cost, high performance, reliable, scalable supercomputing cluster. We also are going to be providing analysis, automation, and documentation to Sandia Labs, so that way they understand how we build the supercomputer and cluster and how we intend on maintaining it. And we also are going to be providing analysis of power consumption. One of our key points is to be low power, and so we actually want to prove that we are low power by providing thorough analysis of the power consumption and the performance, scalability, and reliability of our system. That one, yes. Yep, got it. Alright, so the engineering requirements, they reflect our marketing requirements. The first one is automatic detection of the number of nodes in the cluster. Our primary node is going to be controlling anywhere up to, I think 98 was our top number of nodes, of which it's going to be, right now there's 3 hooked up to it, and it can tell that there's 3, and hopefully when we hook up more, it'll be able to tell there's more. There'll be an automation script that sets up each new Jetson board and adds it to the cluster. All processes, downtime decisions must be documented, detailing what went wrong, troubleshooting with processes, and the solutions to what happened are. Next slide. The cluster must be portable and able to move given 30 minutes notice. We are using a server rack with wheels, so actually should be pretty easy to move around. And a node should be able to communicate at a speed of at least 10 megabits per second through the Ethernet with the other nodes in the cluster. Constraints. We are required to make the boards from the NVIDIA TK1, required to make the clusters from the NVIDIA TK1 board, which are being provided us by Sandia. We also must build a cluster that is able to run open MPI programs, since this is what we are using to test the performance of the supercomputer. And the cluster must have the ability to have statistics of each node grabbed at any time. Alright, criteria. Our time taken to set up and take down the supercomputer should not exceed 30 minutes on each end. Also, the total power requirement should not exceed 11 watts per board. And to determine the cost, power usage, and performance of the Jetson TK1 supercluster through analysis of the performance. So, user experience. Our supercluster is going to be, our supercomputer is controlled by a single master node that has access to all other nodes through a text-based user interface. Analytical scripts are going to be provided, are going to be used to provide performance data on the supercomputer, and we will be providing documentation and analysis of performance data. So we're going to have, monitor, keyboard, mouse, standard computer setup hooked up to the main board, where the user can then access all the other nodes through the main node. Next. So people who are interested in this type of project, obviously Sandia National Labs, and we're going to be providing documentation and analysis to them about these boards, but other people who would be interested in a low-power supercomputer would be scientists, startups, and people who are environmentally conscious. This is mostly because all these people tend to have limited funds, and so having a supercomputer that isn't taking up kilowatts of power would be useful if you have a limited power budget. Also, less power, less damage to the environment, less burning fossil fuels, all that good stuff. So environmentally conscious would be very happy about this.
So now I want to dive into the hardware with you all. So before I get into the nitty-gritty details, here's a nice little overview of what the rack is going to look like. Right in the center, we're going to have a power supply tray that will be powering all of the boards. The yellow or orangish lines there you see are going to be trays of boards. And then you see two blue rectangles there, which is where our two switches are going to go. If this picture doesn't do it for you, I want to direct you over there to that corner, where not only have we constructed the rack, but we've also proven that the switch fits inside it. Check there. But what I'm really here to talk to you about is power. So as we're going into this project over the next quarter, you might know me as Will, but you may as well just call me the power guy, because that's what I'm here to do. So going on to the next slide, this is pretty much a justification for our power. So what's nice is the NVIDIA Jetson TK1 board is very highly documented, but we also have proven this ourselves. So right here is just some power values that justify some of the criteria we have. Namely right here, it says just under 11 watts of peak DC performance. And so over here on the left, I have some calculations. If one NVIDIA Jetson board is at 11 watts at 12 volts, 24, which is approximately 1/4 of the boards we'll be using, 264 watts, and then the total power of all boards is going to be just over a kilowatt. Down at the bottom, you can see that one board is going to peak at just about 0.9 amps. Scaling that up, we get 22 amps for 24 boards, and then 88 amps for 96 boards. So some of those numbers seem pretty high, and so this is just, I guess, a spread of all the numbers to decide where we're going to go with power. So moving on to the next slide, this is the solution that we've come up with. So we've decided on 24 NVIDIA boards. That's 264 watts on each power supply. That's a more manageable number than if we had done one power supply for all of the boards in total. The peak there is going to be 22 amps. And so each power supply is essentially going to be powering 24 to 23 boards, depending on our switch constraints. And so going on to the next slide, the justification for this solution. A single power supply is a single point of failure. So the more you have, if one power supply fails, you're going to have a more reliable system. However, if we wanted to just go on that route, we could have just kept it with 100 power supplies that come with each board itself. However, then we have 100 plugs to go into the wall, coming into some other issues. 4 power supplies spread the total current into the 4 wires, as opposed to having 88 amps on a single wire. And so over here you can see the gauges of wire and how much current they're rated for. And so we're currently going to need an 8-gauge wire. However, if we decided to use only a single power supply, we may have to move all the way up to 2-gauge wire, which quite frankly I don't know if I could solder. And then finally 500 watts was chosen because PSUs are generally most efficient at 50% load. And assuming that at 11 watts peak or 10 watts on average under load, each power supply is going to be utilizing just under 250 watts of power, which should keep it at about 85% efficiency with the power supplies we have chosen. Down at the bottom, there's our design matrix for the power supplies, but again, all it does is show that as you spread it to more and more power supplies, you start to lose some of that, some of that reliability pros with some efficiency cons. And so that's why we decided to use 4 500 watt power supplies to power the system. Moving on to the next slide, we'll go into the network setup.
So then, for the other part of the hardware setup, we obviously need a network to connect all the boards together. So the two major components are switches and Ethernet cables. We decided to use Ethernet because it's very easy to set up and it's cheap compared to other forms of connecting the boards, such as serial and more expensive like fiber. So the main considerations we had were whether the ports on the switches, we can either use a very large switch or a very small switch, which would connect smaller boards, which reduces our point of failure since there's only 16 boards per switch and the switch fails, we might only do 16 boards. But then the cost of a larger switch is significantly cheaper than buying a bunch of smaller switches, so we decided to go for that. So next slide. So for how we set up the switch, there's two main ways we can set it up. I'll talk about the right first since it would have been the preferred way to set it up, but we chose to do it this way because we only ended up having around 100 boards. So preferably if you wanted it to be scalable and to maintain consistent speeds between all boards, you would have a group cluster of boards connected to switch, and that connected to a switch that will connect all your other switches together. That way, the speed of each Ethernet cable does not increase as you increase the number of clusters. Like in this setup, you'll connect all the boards to switches will connect to the next switch, which will connect to the board, and you'll keep chaining the switches down, which if you want to connect from the board, from the first switch to maybe the last one, the time will take longer and longer the more clusters you add. But we decided to use this setup because we only have 100 boards and we decided to use 48 port switches. So then this setup makes it a lot easier for us to connect, and we can't really use that setup because we would need another switch and that would increase cost. And then for the speed of the switches, we decided to go for a 1000 megabit per second switch. That's configurable, so we can, in the end, we should be able to test if the speed of the switch will actually affect our supercomputing cluster. Next page. So then our software review is it's very straightforward. We have a main board, we run open MPI code, which basically allows the code to be parallelized across all the board. All it does is send the code to all the other boards and then returns the data you get to the main board. So then our major components of the software will be how we manage this cluster, which will be how we get GPU data, maybe CPU data, and then network traffic. We'll have a file system that will connect all the boards together so we can share the code between all the boards and have them all run the same code. And then the mini apps is a constraint given to us by Sandia, which is just the benchmarks we have to run our cluster. Next slide. So then our cluster management, we narrowed it down to 3, which is ROX, Chef, and Ganglia. ROX we quickly decided not to use because it has no ARM support, and our Jetson boards is an ARM-based processor, so we can't use that. Chef looks very good. It allows you to run scripts to all your other boards too, but then we looked it up and it costs money, so we decided not to use that. And finally we got to Ganglia, which is free, it's scalable, and it's suggested by NVIDIA, so that was our choice. Next slide. So Ganglia, it's very easy to install. It's basically a package. You can just app-get it on any Linux-based computer. It monitors both CPU and GPU. It has a very low resource cost because it runs in the background, and you can set a timer to say like 50 seconds, and it'll send data back to the main board every 50 seconds. And it's scalable because all you need to run on a client is you run a simple monitoring service and point it at the IP of the main cluster, and it'll just send packets every once in a while. The problem with Ganglia is that it does not allow you to run scripts to all your other boards. So then things like Chef, you can configure it. You can say, here are some scripts I want you to run all the boards connected to my device. Ganglia cannot do this, but we can supplement this by writing our own scripts that will basically do what Chef would have done for us. Another good thing about Ganglia is it actually exports the data in either XML or JSON format, which will make it very easy for us to format it or present it in any way we want. Ganglia also helps us to keep track of which nodes are up and down, and the resources used on each node individually, so it can generate graphs for each node individually. It keeps track of this data for as long as we want, basically, and it stores it all in a database of your choosing, so you can use MySQL, you can set up metadata. Next slide. So the additional to cluster management, and I might talk about, is we definitely need scripts, so we would like to plug in a new board. It should just set everything up by itself. It should get an IP assigned to it by the main board. It should have all the file systems, all the packages it needs. This is something we're still working on. We're still thinking of whether we want to create an image to flash to the board, or we wanted to maybe set up a cache for the packages for all the boards to hook up and grab. But this is definitely something that will be a big part of the project, and we are still working on this. Next slide. And then the next part is our file system. There are 3 main file systems we looked at, which is a network file system, NFS, that's very popular. It's built into all Linux kernels. It's very easy to set up. It hasn't changed for years. There's Orange FS and Lustre, which are both designed to work with parallelized computing systems, but then they require more. They take longer to set up, especially Lustre, which requires a kernel module, which will require us to reflash most of the boards. So next slide. The first one we'll talk about is the network file system. As I said, it's very easy to set up. It's built into the Linux kernel. I think the latest Linux kernel has it already enabled, so you just enter it as version 4, you just run it, install it. It's very simple. It works well with Unix systems, as I said, it's built into the Linux kernel, but it does require a moderate amount of resources per node, since for the benchmarks we run, it requires read-write permissions. So every time you run a benchmark, there's a lot of network traffic. One way to reduce this is we can force NFS to use UDP packets instead of TCP, which will greatly reduce the network traffic. But we are definitely going to be looking at Lustre or Orange because they're designed for parallelized computing systems, and these seem like a better choice. Yes.
Alright, so to briefly talk a little bit more about NFS. One of the bigger downsides about NFS is that the entire storage is only hosted on one machine on one drive, which in this setup could cause a bottleneck when all of the other boards are trying to access a single file. So one of the benefits of both Lustre and Orange FS is that they try to distribute multiple files across multiple nodes across the network, as well as also spread out all the metadata for all of these files. So, which makes it a very parallelized distributed file system and can alleviate any sort of bottlenecks which could incur from only using one board and one hard drive as the network file system. Lustre, as Sean mentioned, requires a kernel module and requires a patch to run on ARM. But Lustre has already been being used on 60 of the 100 fastest supercomputers, which shows its scalability and resilience. And Orange FS has very much the same ideologies of dispersing the metadata and the data across multiple computers. And also Orange FS has a very nice guide as far as how to very easily build and set up, and doesn't have any ARM issues like Lustre does. Unfortunately, there isn't as much documentation, so if we run into issues, it could be a bit more of an issue. So for right now, we're going to stick with NFS, and then as we get there, we'll test with Lustre and Orange FS to see if that alleviates any sort of bottlenecks. So we built a supercomputer. What do we want to do with it, right? We want to actually be able to test it and give real-world numbers of its performance. So the tools that we're going to be using is a suite of benchmarking tools called mini apps, being developed by Sandia, and these tools are actually derived from real problem sets. So, for example, one of the ones that I came across was in circuit analysis tool, kind of like PSpice, and I thought that was pretty cool since, hey, we're all CPEs here. So, each of these tools have come in different flavors for different sort of distributed architectures. The ones that we care about are the ones that are built using OpenMPI and CUDA. Since these Jetson boards have 192 CUDA cores, there's a huge possibility for distributed computing. So we can run all of these benchmarks on a different number of boards to see how scalable each of these tests are individually. We can also collect the power consumption data across all of the boards to see how much power it uses for any given test. As well as with the Ganglia, we can see the CPU and GPU usage, network traffic. I think even memory management and hard drive usage. And so the goal is that with all of this data that we can compile it all into a very clear picture of just how low power, highly scalable, and high performance this cluster that we built is.
So our test procedure is relatively simple. For the first two, the connection test and the power test are actually very straightforward. For connection test, we can either ping all the boards to see if everything's connected, or just run nmap, which will tell us if all the boards are connected together. For the power test, we can almost just confirm that visually. If the lights are on, that means the power's working. But we also have a power analyzer that will tell us how much power the entire system is using, and we'll hopefully use that to make sure that all our power calculations are correct. The third step is to run benchmarks, which, as Garrett explained, is just getting data. So we'll run all the benchmarks, hope they all return correctly, and that should be fine. And the final one, we'll probably test the recovery test. We're going to see what happens if we unplug a board and see if our cluster can recover itself from this state and continue the calculations or benchmarks, even if a few boards are down, or if we lose a whole cluster, it should still function and reconnect itself if possible.
So where we are right now, currently we've actually gotten, so we have 4 boards with us, and so we got all of the Ganglia, the OpenMPI, and running benchmarks on the cluster working, and so what we need to do now is make the script so that when we get all the other boards, we're able to all convert them into compute class nodes. And then we also need to put together all these wires, so about 100-ish boards. It's going to be a lot of soldering. You have the barrel connectors to put onto the little wires, the 14 gauge ones, and then you got to connect all that to the 8 gauge while making it so that it's manageable, because we don't want a rat's nest of wires going around. And so then once that's going to be happening, the scripting and the power stuff, and then also Ganglia, taking the data that we've already gotten from Ganglia and then making a type of document from that. It's going to be done over December, and so once we get back, we should hopefully have all of our stuff delivered to us. So then that weekend we can build it and put it all together, and then we'll have about 6-ish weeks to run the cluster and do different tests on it and document. And while doing that, we want to be able to document any of the failures. And then at the end, we'll make sure that our analysis is correct and compile all the documents together for all the different tests to give to Sandia. So for our bill of materials, we would like to get 94 boards, because you have 48 ports, so that's 96, and then 2 less because you're connecting the 2 switches together, so that's 94. We want to have the 4 boards still, so like if something goes on, we can use a smaller cluster to play with it to see like, hey, can we reproduce it, and stuff like reproduce issues. And then this is the 1 gigabit switch that we're going to go with, the TP link. It's pretty cheap, and it also has the ability to be configurable, so you can go from 1 gig to 100 megs. And then the power supply that we went with is the 80 plus bronze, the 500 watts. The bronze rating means that it does 85% power efficiency. We're thinking about getting the platinum level one, but because it's just a simple bell curve, you can just tell off of the data that you're already getting. So the bronze is just to test with low cost currently. And then our baking rack that we have in the corner working. Yeah, they're a lot cheaper than actually getting a full server rack to make. And then on the next slide, we have all the other just random things that we need. So we need like plywood, 100 different Cat6 cables to connect all the boards together. We need the barrel connectors because we don't want to cut the power supplies that are given to us, because that would be wasteful. Then all the other things. So for concluding remarks, we said a lot, so kind of just want to go over what we're actually doing. Create a low cost, low power, high performance, reliable, scalable supercomputer cluster. Document all the downtime and decision and procedures, and benchmark it with Sandia's mini apps. And because we've gone through all the different variations that this cluster could be, go to the next slide. This is just a summary to show exactly what we're going to be using for this. And then, questions?
Is heat management any concern with this project, or is it?
So for one, we'll be in winter quarter. It's a pretty, the building gets kind of cold. Each board itself has a small fan on it, and then the power supplies do as well. So we envision it not being an issue, but if so, right now the potential quick fixes are just fans on the outside to kind of just increase airflow. This building does get cold in March.
No heating in the EE building. Sure you are aware.
Any other questions?
All right, thank you.